Hello everyone, welcome to episode 1 of Hyperbolic Geometry. Today we're going to cover hyperbolic plane and hyperbolic lines. And first note that there's many models of hyperbolic plane, so we will begin with one simple one, which is known as upper hyperbolic plane, upper half plane model. So it's defined as following: hyphen h is equal to a complex number c, such that imaginary part of c is greater than 0. So let's draw a picture. So in a complex numbers c, the hyperbolic plane is only the upper half plane. And the hyperbolic line is defined as the following. So hyperbolic line in H is two-way, is the Euclidean line. In the complex plane that is perpendicular to the real axis. In C. And also, the other way is the Euclidean circle center on the real axis. And of course, this is all the intersection of the intersection in H. And so that's the second bit. So let's have a look here. So those are all hyperbolic lines. Let's call them L1, L2, L3, and L4. So the next, we begin with next is the definition. Two hyperbolic lines L1 and L2 are parallel if they do not intercepting each other. So in the example above, we can see that L1, L2, L1 is parallel to L2, L3, and L4, but L4 is only parallel to L1 and L2, but not L3. So yep. So next we're going to cover that a proposition that for each pair P and Q of distinct point, in the hyperbolic plane H, there exists a unique hyperbolic line L in H passing through P and Q. So we will doing that in two cases. The first case is the hyperbolic line is indeed a Euclidean line passing through P and Q, and the second case is so the first case P and Q, the Euclidean line passing through P and Q, and the second case is the Euclidean circle passing through that P and Q. So case 1, if the real part of P is equal to the real part of Q, then there exists a unique Euclidean line L such that Z is in complex number C, such that the real part of C is equal to the real part of P passing both P and Q in Euclidean geometry. Then L is equal to capital L intercepting with the hyperbolic plane is the unique hyperbolic line passing P and Q. And case 2, if P and Q is the real part of P and Q is not equal, then there exists a unique Euclidean circle passing through that. The idea of that is we draw a line segment LPQ passing through P and Q. Then we can draw a perpendicular bisector K, that perpendicular to the line segment PQ, and divide PQ into two equal parts. Then for any points in K, there's always a unique Euclidean circle passing P and Q. So in particular, the point X in K intercepting the real part would give us a Euclidean circle. So okay. So now let's write it down. Suppose the real part of P is not equal to the real part of Q, then let LPQ be the Euclidean line segment passing through P and Q, and K be the perpendicular bisector of LPQ as drawing above. And since the real part of P is not equal to the real part of Q, then we know that K is not perpendicular to R. We know that K is not perpendicular to R. Then K and R intercept at a unique point X as shown above. Then we can let A be the Euclidean circle at X with radius P minus C, P minus X. So A is the following complex number C set in C such that Z minus X square is equal to P minus X square. And clearly, this A is unique because we have only a unique point X with a fixing radius, and A passes P since X is in K and X minus P since X is in K. And since C X minus P is equal to X minus Q, then we can say that then Q must be in A. Therefore, we can say that L equal to A intercepting the hyperbolic plane is a hyperbolic line passing through P and Q, and since A is unique, therefore we can say L is unique hyperbolic plane H. And thank you for watching. That's all I got for today, and I see you guys in the next episode.